For one-to-one mentorship, fill up the form provided in description of this video. Hello everyone, today we are going to talk about a very important topic, that is expression of kinetic energy. We discussed about KTG in last lecture. This lecture is part of that series only. And first, to understand this, we'll write about the kinetic gas equation, which we discussed in our previous lecture. What is the kinetic gas equation? It is PV is equal to 1/3 of mass multiplied by total number of particles multiplied by square of root mean square speed. So to understand it further, we will write the PV is equal to nRT, which is 1/3 mn u square RMS. Number of moles can be written as total number of particles divided by Avogadro number, right? So from here we can cancel out capital N. So after cancelling out capital N, we'll get capital R divided by Na times T is equal to 1/3 of small m u square RMS, right? So R by Na can be written as K, which is Boltzmann constant, that is gas constant divided by Avogadro number. On further solving it, u RMS will come out to be 3 times under root of 3 times KT divided by small m, right? So this is the expression for u RMS. We discussed about this in previous lecture as well. So KT can be written as 1/3 of m u square RMS. M u square RMS can be written as 3 times of KT. If we multiply it by half on both the sides, we'll get half of m u square RMS is equal to 3 by 2 times of KT. This expression can be written as kinetic energy of one gas particle, right? So we got the value of kinetic energy of one gas particle, that is 3 by 2 times of Boltzmann constant multiplied by temperature. Now we are going to talk about molar kinetic energy. It is total kinetic energy of all particles present in 1 mole of gas. So we'll write kinetic energy of 1 mole will be equal to kinetic energy of Na particles. Since 1 mole is basically Na particles, so we can write it as kinetic energy of one gas particle multiplied by Na, right? So we got kinetic energy of one gas particle 3 by 2 times of K times of T multiplied by Na. We know that K is basically R divided by Na, so R will come out to be K multiplied by Na. So we can write kinetic energy of 1 mole is equal to 3 by 2 times of RT. We can similarly write that kinetic energy of n moles of particle will be 3 by 2 times of n times of RT. This is very important. Now we'll talk about different types of molecular speed. These are root mean square speed, average speed, and most probable speed. The expression for root mean square speed we discussed in last lecture as well. Under root of un square plus u2 square up to un square divided by total number of particles, that is n. Similarly for u average, it is u1 plus u2 up to un divided by n. For most probable speed, there is no such expression. On simplifying further, we can write root mean square speed as u RMS is equal to under root of 3 KT divided by m. U average can be written as under root of 8 KT divided by pi m. Similarly, u most probable can be written as under root of 2 KT divided by m. U RMS can also be written as under root of 3 RT divided by capital M. U average can be written as under root of 8 RT divided by capital M. 8 RT divided by pi m. Similarly, u most probable can be written as under root of 2 RT divided by m. U RMS can also be written as under root of 3 p by d. Similarly, u average can be written as 8 p divided by pi d. Similarly, u most probable can be written as under root of 2 p by d. If we find the similar expression here, that is 3 is repeated for root mean square, 8 under root of 8 by pi for u average, and under root of 2 for u most probable. So if we take out the common factor in all these, we can simply find out these values and check out which is the highest and the lowest. So u root mean square is greater than u average, which is greater than u most probable. Now we solve a problem here. Equal mass of same gas is contained in the following 3 containers at same pressure. What will be their order of root mean square speed? So we have 3 containers: cubical, cylindrical, spherical, and dimensions of each are given. So we know that moles of gas in all containers is the same because the gas type is the same and the mass of gas in each container is the same. So we can write under root of 3 p by d for u RMS. If we calculate the volume in each container, it will come out to be for cubical 1000 centimeter cube, for cylindrical, that is pi r square h, 1000 pi centimeter cube. For spherical, it will come out to be 4000 by 3 pi centimeter cube, right? So we know that density is basically mass divided by volume. If volume increases, that means density will decrease, which simply means that uRMS will increase. So we can simply write our answer that uRMS for spherical will be greater than uRMS for cylindrical, which will be greater than uRMS for cubical, because uRMS should be in same proportion as volume, whereas in inverse for density, right? So moving further, we'll talk about an important note, that is in KTG we always take SI units. So we'll talk about the SI unit of important terms. So for temperature we use Kelvin as the SI unit. For mass, that is kilogram. For R, that is gas constant, it is 8.314 joule per mole Kelvin. This is the SI unit. For Boltzmann constant, it is 1.38 multiplied by 10 raised to power minus 22 joule, right? K is basically R divided by Na. If you solve, we'll get this value. For pressure, we use Pascal or Newton per meter square, and for different expression of pressure, we can write 1 atm is 1.01325 into 10 raised to power 5 Pascal. 1 bar is 10 raised to power 5 Pascal. Density is kg per meter cube. 1 kg per meter cube is 10 raised to power minus 3 gram per centimeter cube. 1 kg per meter cube is 1 gram per liter as well, right? And now we'll solve a problem here. Find root mean square speed in meter per second of hydrogen in following condition. First, 2 mole of hydrogen gas at 300 Kelvin. So let's solve this problem here. So solving the first problem, we have hydrogen gas. The mass is provided, that is 2 gram per mole. The molar mass we know 2 gram per mole, and for first problem we have to find the root mean square speed for 2 mole of hydrogen gas at 300 Kelvin. You know that uRMS is under root of 3 RT divided by capital M. 3R, that is 8.314 multiplied by 300 divided by 2. We have taken the SI units here. So similarly for molar mass, we can write 2 gram per mole as 2 into 10 raised to power minus 3 kg per mole, right? So on solving further, we'll get uRMS in meter per second. Now we'll talk about the second problem here. 3 mole of hydrogen gas in 5 liter container at 1 bar pressure. 1 bar we know it is 10 raised to power 5 Pascal, we discussed earlier. So we can write 3 mole hydrogen gas in 5 liter container at 10 raised to power 5 Pascal pressure. So here different expression will be used for uRMS, which is under root of 3P divided by D. Pressure here is 10 raised to power 5 divided by density. Density here will be mass divided by volume, we know. So mass provided here will be moles multiplied by molar mass. So moles here is 3, molar mass is 2 gram per mole, and divided by 5. Further solving it, density will come out to be 6 by 5 gram per liter, which will be 6 by 5 kg per meter cube. So uRMS can be written as under root of 3 into 10 raised to power 5 divided by 6 multiplied by 5. Solving further, we'll get the value, that is 500 meter per second. Now solving third problem, 4 mole of hydrogen gas having density 1 gram per centimeter cube at 10 raised to power 5 Pascal pressure. So 4 moles hydrogen gas, density is provided, that is 1 gram per centimeter cube at 10 raised to power 5 Pascal pressure. So uRMS, different formula will be used here, that is under root of 3P by D. So talking about pressure, that is 10 raised to power 5 Pascal divided by density. Density, here it is 1 gram per centimeter cube, which can be written as 1000 kg per meter cube, right? Simply put this value over here, 3 into 10 raised to power 5 divided by 1000. It will come out to be 17.32 meter per second. So this will be our answer. Average kinetic energy per gram of gas at given temperature is given by 3 by 2 RT divided by molecular weight. This is the average kinetic energy per gram of gas. And for one-on-one mentorship, simply fill up the form in description.